All right, here we go. We are now looking at Unit 8, Lesson 3. This on our formula sheet kind of has to deal with kind of like this middle section on this second side. So we have correlation, causate. Oop, that's supposed to be a square. Let's try that again. Okay, so we have correlation, causation, equation of a line, and this thing called the correlation coefficient. This is kind of what we're looking at today. All right, let's begin with the word correlation. All right, so again, correlation. Well, correlation is the relationship between two different things. And so you can come up with some easy examples of that. So how two things are related. Like for instance, the temperature. All right. Right. So the temperature and the amount of ice cream sales. All right, the temperature and the amount of ice cream sales. The warmer something is, the more ice cream sales that there are going to be. Because people are just going to go out and buy ice cream. Or let's talk about the number of hours you work and the amount of money you get paid on your paycheck. The more hours you work, the more money you should have on your paycheck. Or you could have a negative, like okay, so kind of talking in a negative fashion, the number of hours you study and your grade. Okay, if you study less hours, your grade is going to be lower. Okay, study more hours and it would be higher, et cetera, et cetera. All right, so these are correlations, and because they go in the same direction, they're technically called direct correlation. Okay, now you can have an opposite direction. The number of hours you work out, okay, work out at the gym, and your weight, or something like that. The more hours that you work out at the gym, the less you'll weigh. So that is, because again, these things do have an effect on each other. Okay, they do have an effect on each other. Well, shoot. Use the exact same idea. The number of hours you work out at a gym, if you don't work out very much, and your weight, you might tend to weigh a little bit more than somebody who would. All right? So these are all related. These things have an effect. These things are related, okay? And these last ones would be an inverse correlation. All right. So that's what correlation is. Now, just because two different things have something to do with each other does not imply our second vocabulary word of the day, causation. Causation means one thing literally causes the other to occur. Okay, one thing causes the other to occur. Now, two things can be related, but doesn't cause the other. So, for instance, So again, the temperature of day, okay? The temperature. All right? And the amount of ice cream sales. All right? All right. Just because the temperature is up doesn't necessarily mean that more people just naturally are going to need ice cream. Okay, it isn't built in our DNA or anything like that. So it doesn't cause ice cream sales to go up. The temperature doesn't cause ice cream sales to go up. Now, they might go up, but it doesn't mean that it's necessarily caused. Okay, another one is, okay, here's one. Ice cream sales and the number of sunburns. Okay? So if a city or whatever happens to have more ice cream sales, did that cause that city to have more sunburns in that city? No, that doesn't cause sunburns. Ice cream doesn't cause the sunburns. Okay, it doesn't cause, but they are related. They're both probably related to the amount of sun that a city particularly gets. If it's really like sunny and warm, yeah, ice cream sales are going to be up and sunburns are going to be up. It's just the way it is. All right. So now the ice cream didn't cause the sunburns, but they would be correlated because, like, when one goes up, the other will go up. When one goes down, the other will go down. All right. So they are correlated, but one thing doesn't cause the other. So that's the first thing. Correlation means that they're related, and then causation means that one causes the other. Okay? So what they do is they start us off with a bunch of statements that the thing is correlated. So that's not a question. Okay? All of the things are correlated. All right? Now, our mission is there enough evidence for causation? All of the things are correlated, but is there enough evidence for the causation? Right, so are they just correlated, or is one also causation? Okay, the number of additional calories consumed and the amount of weight gain. That is causation. The amount of calories you eat directly links to the amount of weight somebody gains or doesn't gain. That is a direct link. The amount of cars a salesperson sells, all right, and the amount of commission. Commission is like money upon sale. So if you sell something, you kind of get like a little bonus. That's what a commission is. So yes, if a person sells more, they will get more commission. If a person doesn't sell stuff, they're not going to get paid. If a person sells stuff, they're going to get paid. So that's what a commission is. All right, so the age of a child and their shoe size. Now this one is kind of close. Okay, but I think that is just a correlation. All right, just because somebody is older doesn't necessarily mean that their shoe size is larger. And my kind of reasoning behind this is, think of, like almost like adults. All right, think of adults. All right, say a person is size 9. Okay. Can you tell how old that person is just by knowing that they're a size 9? Okay. I can't tell how old that person is because they're a size 9. Now, they say that this is a child, so I can maybe kind of understand a little bit more that, yes, children's shoe sizes kind of dictate the age a little bit, but putting that into a child sense, okay, because I don't know even children's sizes, like size 12 or something like that. Do you know how old that child is now? I don't. So I think they're just a correlation, not a causation. All right. The number of cold, snowy days and the amount of hot chocolate sold. Yes, they are both going to go up. If there's more snowy days, cold days, yes, there's going to be more hot chocolate. However, cold, snowy days don't cause people to buy hot chocolate. You know, it's not like we're DNA like driven to do that. So this is just correlation. All right, now, the next item, if you look at our side formula sheet, is the correlation coefficient. What a correlation coefficient is this. It's denoted by the letter R. All right, and what this is this is on a scale from 0 to 1. Okay, 0 is very, 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 very weak, and 1 is very, very, very strong. Now, what do I mean by strong and weak? Okay, this has to deal with what is known as a scatter plot. What a scatter plot is just a bunch of dots that exist. All right, so here's an example of a scatter plot. Now, if I were to draw what is known as a line of best fit, what you do is you try to draw a line through those dots. And wherever those dots happen to be, you draw a line that goes with the dots, through the dots to the best of your ability. Now, with this line of best fit, the question that you need to ask yourself is, how close are the dots to the line? How close are the dots to the line? Are they really, really, really close? Like, are they on the line? Or in general, are they kind of far from the line? If those dots just so happen to line up on your line, that's really, 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 really strong. You're going to have a correlation coefficient that is extremely high, like close to the number 1. Okay, that's a very, very strong correlation coefficient if the dots are really, really close to the line. If the dots are typically really, really far from the line, like this is my best guess at what the line is. If our dots are really, really far from the line, then our correlation coefficient is going to be really small. Okay, so 0 is weak, which means the dots are really, really far from the line. One is strong, where the dots are pretty much smack dab on the line itself. See if I can kind of put this up here. Okay. Easiest way here. That's really strong. That's really weak. And again, this is on a scale from 0 to 1. Now, second thing that you kind of need to know about a correlation coefficient is this. So these green lines, the line of best fit, okay, is technically called the least squares line. This line, if this line goes uphill, just like a normal line, it has a positive slope. It's going to have a positive correlation coefficient. If the line goes downhill, then it will be negative. Still on a scale from 0 to 1. Right? Still on a scale from 0 to 1. So if I have a correlation coefficient that is like positive 0.85, that means it's strong and in a positive slope. So that means the dots are pretty close to the line, and the line generally is positive. Where you could have a correlation coefficient of negative 0.85, which means the dots are really close to the line, but the line generally is going downhill. Okay, so the dots are pretty close to the line, but it goes downhill. Okay, so here we have the same pictures for all of these different things. All right, this first one is very, very difficult for me to draw a line. I really can't. The second one, this is kind of what I'm thinking. This is what I'm thinking. And then maybe like that, maybe. Okay. So that is the general gist of the correlation coefficient. So that's what that is. Okay. So here we go. Here they want a correlation coefficient equal to 0. That means it's really, really, really incredibly weak. Really, like you can't hardly draw a line. So the weakest one there is A. I can't really even draw a line, it's so weak. All right, so again, okay, so this will have a negative slope. And this is pretty weak. Not incredibly weak, but pretty weak. So a negative slope. Okay, so negative slopes. I'm crossing these off, sorry. Those are the only ones with negative slopes, and it's pretty weak. So I'm going to choose the weaker of the two, and that would be C. Those are the only two with a negative slope, and that is pretty weak. Okay, this next one, we have a positive slope, and it's pretty strong. All right, so again, all right, so things with positive, so let's get rid of anything with a negative slope. Ooh, sorry, it should cross out that one. And this one is pretty much at 0. So these are all positive slopes, and this one's pretty aggressively strong. So the ones where the dots are closest to the line would probably be B right there. So it's positive, a positive slope, and the dots are pretty close to that one. All right, so this one is negative, and it too is kind of strong. Okay, it's kind of strong. Okay, so let's get rid of the things that are obviously incorrect. Okay, so negative and strong means the dots are somewhat close to the line. And so that would most likely be E. That's negative, and the dots are pretty close to the line. Okay, last but not least is which equation best fits the data? And that's kind of like the bottom portion of this formula sheet right here. To really get this, you have to pretty much understand the equation of a line. So y is equal to mx plus b. All right, let's begin with b. B is the y-intercept of a line, a y-intercept. Technically, what a y-intercept is, if I draw some random line on here, the y-intercept is technically where it crosses the y-axis, the up and down axis. So this would be like the y-intercept is equal to 3 or something like that. Okay, that is what the y-intercept is. Where would it cross, or where does it cross the y-axis? Okay, that's what the y-intercept is. That's what the b is at the end. And then the other really crazy important letter is the m. M is the slope. Slope is also known as rise over run. So that is like how much does the line go up and down between 2 points, and how much does it go side to side between the same 2 points on the line, If it goes uphill, it's positive. If it goes downhill, it's negative. All right, so this first question, I see that if I were to extend this line out, I would have a y-intercept that would be technically, I don't know, like negative something, -5 or whatever it is, right? This would be a negative y-intercept. So let's take a look at these y-intercepts. The first one has a positive, so it's not at +5. The second one has a positive. That means it's not A. This next one doesn't even have one, so it's technically 0. And the only one that has a negative y-intercept is that last one. So just by knowing the y-intercept, I can identify that this equation would be 2x minus 5. All right, so again, if I'm looking for y is equal to mx plus b, I first begin by looking at the y-intercept, and I see that my line runs into the y-axis right there, which is going to be at 8. The y-intercept is going to be 8. So this first one is out of the mix. This next one, the second one is +8, so that's good. The third one is -8. -8. No, I need it to be +8. Okay. So I have that 8. All right. So that nail tracks down our equation to one of 2 different equations. So let's talk about that slope. What I notice first and foremost is the slope is going downhill, which means the slope itself is going to be negative. Whatever the slope is going to be negative. So the second one is negative, but the fourth one is positive. So by process of elimination, I see that that would have to be the equation. It has a negative slope and a y-intercept of 8.